Good morning, everyone. They just don't listen to me. Maybe, Thomas, you can start shouting. Ha! Good morning, everyone. Thank you for this silent atmosphere. No? Welcome back. We have Thomas today to talk about exoplanets. Neptune, actually. So Thomas has been around for ever, I guess. He did his bachelor's at KU Leuven, but I learned in Kortrijk, so some diversity at least. He did master studies with us, and he's doing PhD also with us in the group of Laying. And as I mentioned, today Thomas is going to talk about planets and specifically about assessing the reliability of hybrid retrieval methods. The floor is yours, Thomas. Go ahead.
Thank you. Can you hear me through the microphone? Okay. Thank you for the introduction, Andrew. It was interesting as expected. So yes, I'm going to talk about exoplanet atmospheres today, specifically the puffy Neptune WASP-107b, which is a planet that sort of has been the star of my PhD thesis in the past 2 years. So a little outline of today. I'm going to give you a short introduction, of course, about exoplanet atmospheres. And then I mainly want to focus on two parts in this seminar, which is how we go from atmospheric detections, so detections of certain molecules and atoms in the atmosphere, to linking that to the properties of an exoplanet. So really going from detection to characterization. As I said, specifically for WASP-107b, I'll come back to why that is an interesting target in itself. But then I also want to talk a bit about how sure we actually are about what we infer for these atmospheres. So how reliable some of the techniques are that we are using, and specifically I want to talk about this hybrid retrieval, which I'll explain as well. All right, so any well-respected exoplanet scientist starts his talk with this plot and tells you that there's almost 6,000 exoplanets that we've discovered so far. And as you know, most of them are transiting exoplanets. So the majority is transit RVs that we detect, and that's also the reason why you get mostly, this is work, yeah, close orbiting, high mass planets. And so, yeah. When you measure transit, you can effectively deduce the radius of the planet. When you do the RV measurement, you can deduce the mass. You can estimate the equilibrium temperature based on the orbital distance and the luminosity of the star. And then you have three properties which we use to broadly classify the planets. And that's where you get the names from hot Jupiters, puffy Neptunes, mini Neptunes, super Earths. That is usually a combination of these three parameters. It's important to note that it has nothing to do with any actual resemblance to solar system analogs. Yeah? So when we say a hot Jupiter, it doesn't mean it's the same composition or whatever than Jupiter. It just means that it's a Jupiter-sized planet which is hot. But in the past years, it's really become possible to go a step beyond that. So beyond broad classification based on density and temperature, so we can really do characterization of the interior, of the chemistry, of the core, of the cloud properties, etc. And so, of course, this plays into a bigger perspective when we're interested in how did these planets form, what is the general structure of these things, and something I won't be discussing at all today, but is a general, big goal of exoplanet science, which is, of course, habitability on other planets. All right, if you want to know more about exoplanets, you can look at their atmospheres. That's really an entry point, a window into the planet. And so far, so this is the same plot as I showed you earlier. So far, we have around 250 detected atmospheres. With over 60 species, and so it's not so surprised that it's mainly, again, to the upper left side of this plot. What is in particular useful is that we use these transiting exoplanets to study their atmospheres, and that can be done in a couple of ways. So this is a schematic which shows you the full orbital phase of a planet. Of course, you have the transit, which we use to detect these things. And then half an orbit later, you have the secondary eclipse, and that's where we can get information on what is the planet emitting, because if the planet is disappearing behind the star, you're sensitive to only the stellar flux. And so yeah, anything between is what we call a phase curve, and that gives you this additional flux. And so all these different techniques, they give you different things you can learn about the exoplanet. But what you can already, I think, intuitively know is that these phase curves and emission spectra, these really rely on thermal emission from the planet. And so it's very useful, but it's mostly for the warmer to even very hot planets that it's useful. And in contrast to that, transit spectroscopy, you don't depend on thermal emission, you just measure the transit depth. And so I'll be focusing mostly on transit spectroscopy, simply because you can go to a little bit cooler planets with this one. And so if you would measure a transit in different colors, so this schematic here, you would actually see that the transit depth is not completely the same for all colors. And that is, of course, not a surprise. That is because of the atmosphere, or the presence of an atmosphere. And how much this varies with color depends on a number of factors. But in general, it depends on two things: how extended the atmosphere is, how puffy or how bloated the atmosphere is, and on the other hand, what kind of molecular or atomic species are in the atmosphere that can give you opacity to form or to give you this variation in amplitude. And so things that control the vertical extension of your atmosphere is, of course, the gravity, but also the temperature. Warmer atmospheres tend to be more vertically extended. And the general mean molecular weight, so that is, if you have a more heavy atmosphere, you actually compress these things. So ideally, you're looking for a very extended atmosphere, low gravity, quite hot ideally as well, so that you can get a good signal when you're doing transit spectroscopy. And so just to show you once again, theoretically you would expect something like this when you plot the transit depth in function of the wavelength. It varies. And so in reality, this is a nice example, I think, a recent example. In reality, it looks something like this. And then, of course, you can relate the transit spectrum to the actual composition of the atmosphere. And I think that's really the crucial step here, is that you can then compare that to what you would expect from models. Yeah, it's of course not a surprise that James Webb has helped us enormously with these planets. And in particular, I want to highlight one thing which I borrowed, not stole, I borrowed from Linus's seminar a couple of months ago, is the huge difference in quality and spectral coverage we get with James Webb. So this is before you get two types of Hubble data sets, so STIS and WFC3, and then here you have in the infrared, you have the Spitzer data points. And it's really hard to tell something, but of course now the picture looks completely different, and that's really nice. I'm not going to go over all possible results we already had with James Webb. I think it would be far too much. But I do want to highlight this one, because that's quite relevant for the things I'm going to talk about today as well, which is the planet WASP-39b, where we discovered sulfur dioxide. And that was actually a direct evidence of photochemistry. And to go a little bit more into detail what this graph is showing, you start with hydrogen sulfide, H2S, and you end up with sulfur dioxide. And the steps in between, basically from H2S, you do a process called hydrogen abstraction that gives you SH, and then another hydrogen abstraction gives you atomic sulfur. And so you just need atomic hydrogen for that, and then you oxidize sulfur into SO and SO2 by interacting with a hydroxide radical. And so what is the photochemical thing here? Well, this hydroxide and atomic hydrogen is thought to come from photolysis or photodissociation of H2O. And so the net reaction, you start from H2S and you make sure you have enough water vapor in your atmosphere, and then you can get SO2 if there's photochemistry. And so that's a really, really nice result with James Webb. All right, moving on. So this was already I think, quite a nice example how you go from atmospheric detection of a molecule to linking that to what is happening inside an atmosphere. And so I want to talk about WASP-107b. WASP-107b is quite a special planet because it has an extremely low density. Why is that? Well, if you can look at the mass, it is about 10% of Jupiter, so that's why we call it the Neptune, actually. It's not completely Neptunian in mass, but it has a similar radius as Jupiter. So that means it's extremely puffy, it's extremely bloated, and that's why it's often, well, it's actually depicted like this, very cotton candy-like. But what's interesting with this planet is that it's also relatively cool. If you remember from what I said earlier, ideally you would have very hot planets because they have even more vertically extended atmospheres. That is good for your signal. But because this planet is already such a puffy atmosphere, it's a nice combination to have with a cooler temperature, because we can still get a very good signal from this planet even at lower temperatures, and that allows us to probe new chemical regimes, right? Because you have in a completely different temperature regime. Yeah, and then this planet is also known to undergo a process called atmospheric escape. So it's losing light elements, mainly hydrogen and helium. And it's actually been shown with observations that you get a signal, an absorption signal post-transit. And so that means that there's some sort of cometary-like tail behind the planet, and that is a combination of course, the orbit of the planet, but also an interaction with the stellar wind of the star, and that is shaping this outflow. So we know that this planet is losing mass as well. And so, of course, we're interested in what is the general elemental composition of this atmosphere, also an explanation for this inflated radius, and the general chemical composition. Okay, so let's start with the HST observations of 2018, which look like this, a very narrow or low spectral coverage. And the main thing these authors detected was water vapor. There's no methane, and I'll come back to you why we do expect methane, but for now it's just a simple detection of H2O in this planet. But it was much more compressed, a much lower amplitude is featured than what we expect. And so that is due to the presence of high altitude clouds. Now you can imagine this as an atmosphere without any clouds. You can actually form this feature over a much bigger pressure range in your atmosphere. But if you put high altitude clouds there, you actually obscure all of the stuff that is below these clouds. And so when a feature from H2O is formed, you're actually forming it in the region above the cloud deck, right? And so this was the two main findings actually of this paper, is that you get H2O, no methane, and then there's compressed by high altitude clouds. Of course, you want to link that to things of the underlying properties, but that was not possible. Why not? When you're trying to conclude something about the metallicity, it's actually a degeneracy between the cloud deck and the metallicity. The cloud deck, if you put the cloud deck higher, you're compressing features. You're compressing features of H2O and other things. And so the amplitude becomes smaller. The same happens is when you're in a high metallic environment. Higher metallicity means a higher mean molecular weight, means that your atmosphere is generally more compressed. And so the features that you're forming in a compressed atmosphere are also much lower. And so from these observations alone, it was not really possible to tell anything more. These authors also did another type of modeling so of the core, and then they were able to constrain for an upper limit of 30 times solar metallicity. So at least we know it's fairly constrained in that sense, but that leaves a big gap. So to come back to methane, when we look at carbon chemistry in H2-dominated atmospheres, and I specifically talk about H2-dominated atmospheres because we're dealing with primordial atmospheres, so not secondary outgassed atmosphere that are very much heavier and are nitrogen-dominated. You can sort of outline the possible different chemical pathways, but what it comes down to is that depending on the properties of your planet, the main carbon reservoir is methane or CO, right? And so we can actually predict, because we know from lab experiments what the chemical reaction rates are, we know the timescales, and so we can actually predict if we're expecting to find CO or methane. And if you do that for a range of temperatures and compositions, you see that WASP-107 is actually expected to be very methane-rich, right? Because it's quite, it's not, the 1000 Kelvin line is typically the boundary that we take for metallicities lower than 30 times solar. And so we clearly expect there to be a lot of methane, which is not the case. And so, yeah, this is a bit of this was a general problem at some point, which you called the missing methane problem, especially was related to planets below 1000 Kelvin. All right, and then came observations of the James Webb, the MIRI instrument, and I've put a lot of faces here because there's a subsection of the faces that worked on this paper, many of you here at the Institute as well. And so the main results of this study is summarized in this figure. This is just the transit spectrum. You can see the data set is plotted twice, just because we did two types of retrieval on this data set. And then at the bottom, you can see all the different contributions of the molecules. And then there's this broad dominating yellow line, and that is the cloud feature. So we narrowed this down to here a big opacity bump around 10 micron, and then a sort of a sloped opacity towards the optical. And so some of the main detections here was, of course, SO2. And so it's very clear that you have two nice peaks here in the infrared. Again, no methane. So you would actually expect a very large contributions around the same locations here as these H2O bands. Again, we don't see methane there. And then, yeah, we could explain these features in the study by a composition of silicate clouds that explain this like 8 to 10 micron feature. So I want to specifically talk about this SO2 detection and then again the lack of methane. What we find is that actually this SO2 is explained by a metal-enriched environment. If we model WASP-107b, you can, well, that's the temperature assumption that we made that is less interesting. Here you can see the abundance profile of SO2, so we express that in molar fractions or sometimes volume mixing ratios, which is just the fraction of number density, so the number density of methane with respect to the total number density of the gas. And then here, you can actually take these models and generate a synthetic transmission spectrum to compare that, how that would look in an actual observation. And so the black line here is the total transit depth, and then I recompute every transit without, every transit spectrum without a certain molecule to see what are the dominant contributions there. And so what happens when you increase the metallicity, you slowly but surely get enough SO2 in these upper layers that you form a very clear double band. And so this is a clear indication that you need some form of metal enrichment in the atmosphere to have actually an observable amount of SO2. And that actually, well, makes a lot of sense if you just look at the chemical pathway. You start from H2S and you need H2O. The dominant factor here is you just increase the sulfur reservoir in H2S when you increase the metallicity, right? So if you more H2S, you get, again, photochemistry, and then you get SO2 again. All right. Yeah, not sure if I have... yeah, I might go over this a bit more quickly. In this study, we also looked at a comparison between the SO2 detection in WASP-107b and WASP-39b. And from models of WASP-39b, so the first planet on which we detected SO2, it was actually predicted that you wouldn't see an observable amount of SO2 if you were to cool down WASP-39b. And so that was a bit of a puzzle why we did see it in WASP-107b. But I'll go over this quickly. That is mainly related to the fact that we have quite a low gravity, an extremely low gravity of WASP-107b. And so the radiation is absorbed much higher in the atmosphere. That enables chemistry, photochemistry there. And of course, what also very much matters is the UV flux, if you're dealing with photochemistry, the UV flux of your star. And so, of course, the difference between WASP-39 and WASP-107 is also crucial in that. And so, yeah, the second main thing was, again, this lack of methane. And that was really surprising, because we actually expected this in the MIRI range. And so, again, yeah, to explain you a bit further what we expect, at least from models, I'm going to explain to you the three different regimes you have in an atmosphere of what you expect from methane in an atmosphere. So this is, again, volume mixing ratio versus the pressure. And you can see the solid line is the outcome of our models, and the thin line is what you initiate the model with, and that's what you would expect under chemical equilibrium circumstances. So that is without any disequilibrating factors. And you have three distinct layers. So in the deep layers where the pressure is high and the temperature is high, you expect thermochemical equilibrium. And so the two lines, they overlap. Makes complete sense. You're in an environment where temperatures and pressures are high, so chemistry is very efficient, and so disequilibrium effects don't really stand a chance. Then we have a region which is dominated by mixing-induced quenching. And this is typical, visible by this constant volume mixing ratio in these regions. And why is that? Well, in these regions you have upward vertical mixing that is competing with the thermochemistry. And so the vertical mixing is actually more efficient. So that means that you're constantly replenishing these layers with methane from below. And the point where this starts to dominate is what we call the quench point. And so this is the point where your expectations from equilibrium starts to deviate from what we see in the model output. And so this actually sets, this little point sets the ratio between CO and CH4, right? So this little point controls how much methane you get in your atmosphere. How much methane you get is then, again, dependent on the temperature. If you remember this plot I showed earlier, that controls the balance. And also how strong your vertical mixing is. So you can imagine much stronger vertical mixing quenches the atmosphere deeper. And then the upper layer, of course, you have most of the absorption of UV flux, and you get photolysis and secondary reactions with the radicals that are a product from photochemistry. And so in this is still the same paper where we had the MIRI observations. We outlined a few options that we thought were possible in WASP-107b, and then that explained this lack of methane. And the first is, of course, if you change the elemental composition, right? I think the bottom figure here, again, showing you the same thing, is most intuitive. If you lower the carbon-to-oxygen ratio and you remove methane from your atmosphere, you get less methane. And the plot here is maybe a little less intuitive. This shows you that if you increase the metallicity, you get less methane. And so if you increase the amount of carbon atoms in your atmosphere, you get less methane, which is quite counterintuitive. What you also change when you increase the metallicity is the underlying temperature structure. You get more absorbers and you get higher heating rates. And so actually the temperature of these higher metallicity models is also higher. And so that's why you get less methane. At higher temperatures, there's more carbon in CO versus CH4. And there's also an indication, of course, via the detection of SO2 that you have a higher metallicity. And a second big option we identified is playing around with this quenching mechanism. If you were to assume that there is a very big heat source in the planet, so a high intrinsic temperature, you get the same effect. You reduce the amount of methane. And if you play around with the strength of vertical mixing, which we typically parameterize as KZZ, it's an eddy diffusion coefficient. That's how we treat vertical mixing in our models. Higher values mean more mixing. What happens is you shift the quench point down, and so the quenched volume mixing ratio also decreases. So stronger mixing reduces the methane content as well. This is another way of visualizing this, which is perhaps more clear. Increase the temperature, lower the amount of methane. There's a bunch of other options which we had at some point good reasons to assume that they were not really relevant. Horizontal winds can have the same quenching effect as vertical mixing, but models show that this will not be too strong, and a bunch of other effects. But these were mainly the things we outlined in this paper. And then came observations with the NIRCam instrument, and they actually found this nice 3.4 micron peak. So methane was found in there. And these authors, they modeled this atmosphere, and they concluded that you do require this combination of a high intrinsic temperature with strong mixing. And so that was nice. That actually confirmed the things we outlined in the first paper quite robustly, because we were able to constrain the deduced volume mixing ratio of this atmosphere to be consistent with the intrinsic temperature and mixing. All right, so that means we sort of a partially complete picture of WASP-107b based on all these measurements. So we know we have a supersolar metallicity based on the detection of SO2. Yeah, I didn't talk about this, but actually there's in this data set a clear CO2 feature in CO, and so you can actually constrain the C2O ratio to be subsolar, so less than 0.5, which is the solar value, which is quite, well, yeah, it's unconstrained in the sense that we cannot exactly pinpoint which value, but we know that it's a carbon-depleted atmosphere. And then the big conclusion was, well, we do expect a high intrinsic temperature and mixing, and that leads to actually secondary conclusion you can make of this planet, because if you assume these results, you can try to identify where this excess heat comes from. An intrinsic temperature that is that high is not consistent with just leftover energy from planetary formation. So that must mean there's some other form of mechanism that explains this. And so this is not work that we did, but another paper did, and they explained it through eccentricity damping, so friction induced by tides. And then you can also make assumptions about the core. So what's really crucial is that you get all of these things right, because that leads to further modeling that is based on these conclusions, of course. So that's the end. Oh yeah, well, we also have high-altitude silicate clouds. So that's the end. We solved the planet. Unfortunately, that's what we thought as well. But we wanted to dig a little bit deeper into how sure we actually are from these results. And in particular, we used this hybrid retrieval method to really see how sure are we from this characterization of this planet. And so this is an unnecessarily complicated plot of a retrieval, which I used to take a sip of water. All right, unnecessarily complicated because it is just how exoplanet people fit models to data. You get your observations, you assume some sort of forward model. The goal of that forward model is to generate an observable, a model spectrum, at which you can then compute likelihoods with the observed spectrum. And so if you do that, you get an estimation of all the parameters that you're interested in. And additionally, people also used it to compute detection significance for certain molecules that they detect. Right? And so you can make different assumptions for the forward models, and these are really the two extremes you can do. Either you can go for a very low computational cost, which means that you parameterize all your models. You assume very simple things like an isothermal temperature profile, constant mixing ratios. You don't do 2 or 3D stuff. Or on the other hand, you can go full-on physics and compute radiative transfer. You can do chemical kinetic simulation, kinetic cloud formation, even 3D GCM modeling. But in reality, the computational cost of the right side here is way too large, so you cannot incorporate that in a retrieval framework. So that's actually the reason people choose a lot for this low computational cost and these parameterizations. And so what was suggested in a paper by Taylor Bell in 2023 is that you do some sort of hybrid approach where you try to include enough physics, but you make sure that the computational cost stays low to actually do a retrieval. And so we based ourselves on this paper, And we developed our own hybrid retrieval, and so this consists of a couple of steps. So first, we compute a grid of PET structures. We feed that into a chemistry simulator, and so that is all done beforehand, so you don't have to do that on the fly during the retrieval itself. So it gives you a grid of 900 models, spanning mostly the parameters that we're interested in, right? Metallicity, C over O, and then intrinsic temperature and KZZ. And then during the actual retrieval, we then make an interpolation based on the necessary combination that you require, and then we do on-the-fly radiative transfer. And so this is quite doable, this is quite computationally cheap, especially also because we don't include any form of kinetic cloud formation. It's just a parameterization, which is what people do, unfortunately, because it becomes even more complicated if you're trying to do this all at once. Yeah, so again, I think I made this clear why we do this. We want to know what we can trust of these results. We're also a little bit interested in how people parameterize these cloud opacities and how that actually affects what you infer, and we just want to understand what these retrieval do. Yeah, so this is a paper that will be submitted on Monday, I think. And I don't want to go over all the results, that will be way too much. I just want to highlight one particular setup and conclude a few things based on that. So the top part of this corner plot shows you these four atmospheric parameters that we assume, and so that gives you that indeed we have a metal enriched environment of about 3 to 4 type solar metallicity. You have a carbon depleted atmosphere. You get a relatively high intrinsic temperature in this setup. It's an important side note, in this setup. And then you get also indications that you need a significant amount of mixing. Just to give you a complete picture what a best fit looks like from this, yeah, the data points are very narrow, but that's the 3 different data sets, so MIRI, NIRCam, and HST. And then you get the different contributions in our best fit model. So there's SO2, there's big water features, CO2, etc. And then this similar pattern, I think you recognize from earlier, is again an assumption here that there are silicate clouds or some other types of clouds that give you a big feature around 8 to 10 micron, and then a slope towards the optical caused by a Rayleigh scattering or some other sorts of scattering. All right, see how I'm doing on time. Yeah, there's a few things I want to highlight. We talked a lot about SO2. You can get, of course, these SO2 features in the MIRI data. You also have a tiny SO2 feature here. And what we really find is that irregardless of the setup that we use, the assumptions that we make in our retrieval, we consistently retrieve a metallicity, and we retrieve a consistent metallicity because we have SO2 features. So one of the main conclusions here is that these SO2 features really break the degeneracy because it's such a strong dependence on metallicity. And so from the moment you have an SO2 feature in your data set, you are normally able to get a consistent result irregardless of what assumptions and cloud parameterizations you use. But then, of course, there's the important side note that is, of course, it depends on what you assume in your forward model in the first place. So if you parameterize during the retrieval and you find it robust in that step, yeah, you have to make sure that you model SO2 in a consistent way. And we know already that this is dependent on the UV flux, but it is also dependent on the upper layer temperature. So this is not the intrinsic temperature, but the temperature in the upper layer. We consistently fit a subsolar value. So again, this is quite consistent with previous studies. But surprisingly, intuitively, we think that this is related to the lack of methane. So this is partially true, but there's actually other ways to get rid of the methane. This is mainly balanced, determined in the retrieval based on a very narrow balance. So let me go back between this large CO2 feature and then multiple H2O bands. And in particular, I'm choosing to highlight this one. So this is the HST and the NIRCam data. So this is without the MIRI data. And so what I mean with a balance, of course, if you increase your C2O ratio, you get more carbon. And so what happens is there's more oxygen that is being locked up in CO2, and of course CO as well, compared to H2O. So if you increase the C/O ratio to a more solar type value, you increase the CO2 feature here and you decrease the H2O band. And so the CO2, the carbon to oxygen ratio that we derive is very, very sensitive to the relative amplitudes of these two features. And then what is also affecting the relative amplitude is the assumption you make here. This opacity sloped, this wavelength-dependent opacity slope here. What that does is if you increase this slope, you push up the transit depth of this H2O feature. And so if you don't include such a slope, which is sometimes done, you actually get an even lower carbon to oxygen ratio. So this is unfortunately an example on how you can influence a bit your what you deduce from the data based on the assumption you make here of the aerosol or the cloud opacity. But anyway, we consistently find a subsolar value, irregardless of the slope. And then the last point I really want to make is that we have this one methane feature to fit, but we actually find, and this is, I think, the main result of this paper, is that it is very, very dependent on the assumptions you make with regards to cloud opacity. And so that's actually not that difficult to understand if you take again a look at this volume mixing ratio plot, which you showed earlier, which gives you clearly a different amount of methane depending on the intrinsic temperature, which is all good. But what we find is that in the retrievals, we also fit a high altitude cloud deck. And so what you effectively do is you also shield all the methane-rich layers. So it doesn't really matter what the intrinsic temperature is and what the resulting content of methane is, you just don't see it. And so we find it very hard to constrain this parameter simply or purely based on these kind of retrievals. And secondly, we also find that what we expect to fit with KZZ is also different. So we know more mixing reduces the amount of methane, deeper quenching. We've said this multiple times right now. But if you fit, or if you put a cloud deck here, you actually see what happens here for high KZZ values. In the region where photochemistry dominates, you also have more mixing. And so there's more material shooting up in the layers that are otherwise dominated by photochemistry. And so actually what you expect is that higher KZZ gives you less methane. Well, we see in these retrievals that we actually fit it the opposite way. We get that higher KZZ gives you a bigger methane feature. And so that means that the conclusions you make based on the retrieved values of these two parameters, you really have to watch out. And so I'll conclude, again, with this same type of figure. We know quite well that this SO2 feature are very robust indicators of metallicity. So we consistently find this in our retrievals. We also consistently find subsolar carbon to oxygen ratio, which is very low actually, based on this relative amplitude of the CO2 and the H2O bands. You have to take into account, of course, the way you consider scattering, because that affects your results. But in general, we find that these are quite consistent in our retrievals, and so we trust them. We think they're quite robust. And on the other hand, values like the intrinsic temperature and the information on the vertical mixing can very much depend on some of the assumptions you make. And so that, of course, is important when you're trying to go and work with these retrievals, work with these results to explain things like tidal heating mechanisms or infer core masses, because these are all based on what you assume here or what you retrieve for the intrinsic temperature. And so these are quite, you have to take care with these ones. And I think that's the last point I want to make. Thank you.
Thanks, Thomas, for an interesting talk. We have plenty of time for discussion. Don't be shy. Oh, Nico.
Thank you, Thomas. Very nice talk. I missed it, but is it understood why the planet is so puffy? Because I guess that depends mostly on the temperature of the gas, and you can infer that, I guess, from the distance to the star and the radius.
Yes, yeah. So there's two types of temperatures that I talk about. It's the equilibrium temperature, which is just the balance between radiation from the star and what is re-emitted by the planet. And then you have intrinsic temperature, which is really the black body temperature of that planet if you remove all the external radiation. And so, yeah, I didn't mention this specifically, but the fact that this is an inflated planet is also consistent with the fact that you have a very hot core. And so there is another indication that this is the right explanation, so the hot core mechanism. Yeah, so that is one of the reasons that is important to deduce this parameter, but it's true. The inflated radius of this planet is consistent with a very hot core that inflates it deep in the interior. Yeah.
All right, thank you. Cool.
Yeah, so great talk, very interesting. I have, again, a question about this inflatedness. So is that also consistent with a planet that would be losing a lot of mass as well? If you have been noticing like extra material around the planet after transit? And like side question, because it's always something that I can't get out of my head when I see such numbers of low density, is couldn't these be biased by the planet having a significant set of rings, for example? And what would it change to the whole analysis of the thing if it's actually not as large as we expect?
I have no clue about rings on this planet. When it relates to the mass loss that this planet endures, it is connected to the intrinsic temperature in a way that assumptions on the core mass and the intrinsic temperature can give you a fit to the inflated radius. What is the third important ingredient there is the metal content of the planet, right? Lower metallicity can explain you with a different intrinsic temperature and core mass, this inflated radius. And so when it comes to the metallicity, the mass loss of the planet is an important role. Because we know that for, I think, 3.5 gigayears, this planet has been losing light elements. And so you would expect quite a significant metal enrichment as a consequence of that, because you remove lighter elements. And there's actually been a paper that constrains the metallicity of this planet not to 3 to 4, but to 43 type solar metallicity. And so it's very unclear how much actually the mass loss of this hydrogen plays a role. And then, of course, you also must question atmospheric metallicity versus bulk metallicity, which is something we don't know. People assume that it's the same thing, but I think we cannot do this. So.
All right. More questions?
Hi, Thomas. Thank you for the really interesting talk. You said much earlier during your talk that increasing the metallicity in an atmosphere, particularly for WASP-107b, can possibly enrich the environment enough to increase the methane abundancy. But then in slide 27, under option 1, you were mentioning that increasing the metallicity could lead to less methane. It's more a question maybe for clarification, but was the idea behind option 1 that by increasing the metallicity but changing the metallicity composition, you can expect more or less reactions that could lead to methane? That's my first question.
Yeah. People change metallicity in different ways, in the sense that you can assume the same underlying PT structure and then change the mixture during your chemistry simulation, and so then you would expect more methane. In this simulation, I hate to use the words, but it's a bit more self-consistent in the sense that you include the metal enrichment from the first step, which is computing the radiative convective balance and computing the PT profile. And then you see that the temperature effect is actually more important, so you reduce the methane content. Does that answer your question? Because I partially forgot, I think.
I think it does. My other question is also, why would you choose the carbon ratio as the thing to change? This is maybe an ignorant question, but...
Yeah. I mean, the C2O ratio is generally very important to talk about planet formation. And so depending on where you assume your planet has formed, if you assume it beyond the ice line, you assume that there's much more carbon with respect to oxygen because you actually condense out the oxygen. So the oxygen is trapped in ice. And so that's why, but again, this is assuming that this small part of the planet, the atmosphere that you're probing, and the C2O ratio that you're deducing from there is consistent with the bulk C2O ratio, and that is effectively something you can relate to planet formation. But so that's why typically people consider the bulk metal enrichment and then play around with the C2O ratio.
Thanks, Thomas. That was a great talk. I guess my question is a little bit speculative, but what is the final fate of this thing? Say, supposing that the star lives forever, I guess it's a G-type star or something, and alternatively, if the star lives a normal life, like, does it strip away its entire envelope? Does it eventually just cool and become normal? And my second follow-up question is, how rare is this kind of puffy Neptune?
Yeah, so your first question, that was actually the initial project of my PhD, to figure out what happens to atmospheres when the star evolves towards the red giant branch, etc.
High pressure question.
Yeah, but I didn't do the research on this. So I think based on the quite strong interaction with the wind already, and I think the mass loss rate, which is of course a little bit uncertain, but if you extrapolate this over several gigayears, a significant fraction of the mass will be stripped away. What happens then when actual star starts to deform and blow and go to, I don't know for sure with that, but I think it can be expected a significant fraction gets torn apart from this planet. Your second question, I forgot already. I'm sorry.
It was, how rare is this thing? Are there many puffy Neptunes that we know of?
Neptunes, no. But there is something called the inflated radius problem for hot Jupiters. And so there, we generally see that you need some mechanism to explain the inflated radii. But for a Neptune-massed planet, not size, Neptune-massed planet, it is quite rare. I think another example is the planet that was discussed in Linus's seminar, which is a little bit larger in terms of mass, but is equally puffed up. So it is quite rare for this mass. But if you go to higher mass, Jupiter-massed planet, you also see this radius inflation. Yeah.
Okay. And I guess just while I'm handing off the mic, so for this final evolutionary fate, whatever it turns out to be, stripped down, completely stripped, whatever, would that final fate be detectable with JWST and tests, or is that too small of a core at that point?
Depends on what we think the core mass is. There's models that give you a core mass of as small as a couple of Earth masses, and in that case, I don't think there's much of a signal to be remained.
Okay. Thanks.
Maybe quick follow-up question on the inflated radius, Thomas. Inflated relative to what?
Yeah, so the hot Jupiter inflated radius problem is related to how much energy is left over from planet formation. So these are typically younger systems. And so if you don't assume that the core is warmer, similar to what we do for WASP-107, you assume the core is warmer, then you would expect a much lower radius, simply because the planet is less puffed up. And so when we say it's inflated, it means that it is a higher radius than what you would expect for a more moderate or lower core temperature.
I see. So it's relative to our theoretical understanding of how
Yeah.
things should look like.
Yeah.
Not sure how relevant that is, but the low mass community, low mass stellar community, they've been facing the inflated radius problem for decades until they realize that it's completely gone when they include magnetic fields in their models. Just saying.
Yeah. Scaring me a little bit, but that's all.
Yeah, so very interesting talk as usual, I would say. So for the missing methane problem you introduced, based on your observations of WASP-107b, would you say you kind of have a solution for this missing methane problem? Is it applicable to other planets where you don't observe methane and you should, ideally?
I wouldn't be bold enough to say that I solved the missing methane problem. Now with James Webb, there was a second lower mass object and also cooler object where we did detect methane, GJ4 something, and I'll get back to you from that. But I think it's undeniable that the presence of clouds play a role in that sense, simply because we detect clouds everywhere. There's very few, or not that I'm aware of, that are completely cloud-free. And so the role of that is undeniable. And then something that I don't take into account in my models is actually the way these clouds are formed. There's been a PhD student here, Sven Kiefer, who also showed that you can actually slightly deplete the methane content during the process of cloud formation, that you lock up carbon in condensate. So I think clouds is the next thing we really need to start get right in these types of models. Yeah.
I want to make a comment. Well, it's a question actually. I don't do comments. But in the low mass star community, you have magnetic fields that exert pressure because you have ionized particles, but this is also true in a planetary atmosphere. Do you have enough charged molecules? Or?
Not in the core, at least. You have in the very upper layer, so in the nanobar regime, you get an ionized gas simply because there you absorb the ionized mixture, and that's how you also drive the hydrodynamic escape from the planet. But I think you're talking about really deep.
Wherever the puffing happens, which would be deep down, right, I guess?
Yeah, I'm not sure. I don't think that you have a very nice ionized gas there.
But, okay, so magnetic fields are probably not the answer then, I guess? But then, so you say that this planet also has this big tail. Is that not like what gives you the larger apparent radius? Or?
Yeah, well, that's a good comment. No, because that is really post-transit. So that's I don't know how many degrees after you get the transit, but the planet is far beyond egress, and that's how you get additional absorption. And that's also detected. You detect a much thinner gas because that's in a different pressure regime of the atmosphere. So what we're probing with really molecular species is the millibar to microbar regime in terms of pressure, while this escaping gas is much at higher pressure and higher altitudes of the atmosphere. Yeah.
Right, thank you.
We still have time for one or two more questions. I'll ask one myself then, Thomas, and it's a vague question. You can actually feel much, a lot of time with it if you want. So, one of my, a respected colleague of mine in the Sloan project has this saying, I'm fitting bad models to worse data. To what extent does that apply here? Because when I see some of your data, when I see the amount of assumptions you put in your models, it makes me just remember that saying.
I've questioned this numerous times during my PhD as well. I don't think I have time to list all the assumptions, actually. But I think in general, I would say there's 4, maybe 5 aspects of an atmosphere that we're modeling, and often people are interested in that, model them separately. So that is the general energy transport, so that determines the PT structure, which we do. The chemistry is a separate thing. What we don't do is have feedback between those two. What you assume when you make a PT structure is that you have some sort of mixture of gas. We assume that in chemical equilibrium, because otherwise we would need to iterate. You compute a disequilibrium profile and you feed that back into the PT structure. Now there has been studies that show that this is affecting the atmosphere with 100, 200 Kelvin. So it's not super drastic, but if you are dealing with something like SO2, which is very sensitive to temperature, you're probably missing something there. So that's one link. There's another thing which I already addressed is kinetic cloud formation. Again, this affects your PT structure and your chemistry. If you have a high altitude cloud deck, you're shielding the lower layers from radiation, and so you're affecting the heating rates and the cooling rates and the photolysis of these rates below, something we don't do because we post-process clouds. And then the entire, which I think is the fourth thing, the entire assumption of 1D atmospheres. We know planets are not 1D objects, especially when you're probing this terminator region. The main difference, or the main issue there is that you're probing a morning and an evening limb. And so then it becomes important to treat the climate, to know how the winds act, to know how much heat redistribution there is, because there might be a limb asymmetry. Now, this was actually observed again in 2024, because everybody was doing WASP-107b in 2024. And it showed that the result of this limb asymmetry due to the winds is about 100 Kelvin. So that is not too drastic. If you go to hot Jupiters and ultra-hot Jupiters, it can be close to 1,000 Kelvin difference. And so if you then use an 1D approximation, you know you're getting it wrong. I can go on, but I think...
No, I think that's good enough, because then it's going to take a couple of hours, I believe, if not more. All right, so we are on the hour. Let's thank Thomas again. Thanks for coming, and see you next week.